Hello everyone, today we will talk about the small signal analysis of the MOSFET. So first let's start out, what is a small signal exactly? So small signal is basically an AC current. You can consider it as AC current. And when you are doing the small signal analysis, every DC current or every DC biasing voltage, it will be grounded. You will consider when you are doing the small signal analysis, the DC voltage or the DC biasing point will be grounded. What is a DC biasing point? So basically, if you have AC current, something like this, you have a peak-to-peak of 2 volt, and you don't really know what is the top point over here, what is bottom point over here. You just know this is 2 volt. The DC biasing voltage is the voltage over here to bias it. Like for example, if the DC bias voltage is 3 volt, then you know the AC current is, the maximum AC current is 4 volt. The minimum AC current is 2 volt, if the peak-to-peak is 2 volt. If the DC biasing voltage is like 20 volt, then you know the same AC current will have a 21 volt peak and a 19 volt minimum. So that's a DC. So for a small signal analysis, we just forget about the 20 volt. We just make it grounded to do the analysis. Let's start an example with a NMOS transistor. Like NMOS transistor over here. This one is grounded. This one, let's give it a. When you are doing a biasing, you can always consider the gate voltage has two parts. The first part is a AC. The second part is a AC. No, it's a DC. And this will be ground. These two together will create a input voltage. When you are doing a small signal analysis, you will make this one ground. We only consider about AC signal. We don't care about DC biasing. But DC biasing is very important for circuit design. And we can talk about it later about how to determine biasing. It's also a popular topic in the interview. So let's first talk about the AC. So let's make this one a 5 volt DC, and this one will be the output Vout, and here will be a resistor or whatever, maybe VDD over here. So we know this one is a gate, higher potential is drain for NMOS, lower potential is source, and we also have a body which is connected to ground. In this case, body and source are the same. So let's draw the small signal. So in this case, let's consider about a low frequency small signal model. What does low frequency mean? Is we don't care about the capacitor, because capacitors are open during low frequency, so we don't really care about it. But for high frequency later on, you need to consider about the parallelistic capacitor. Basically, you have capacitor over here, and we need to add it for the small signal later. But right now, we don't care about it. We just care about the low frequency first. Let's draw the small signal. So you have a gate, you have a source, and the 5 volt is connected to the gate. So in small signal, it's grounded. So it's 0 volt, no longer 5 volt, because the DC is gone. And we have a body over here, positive. So in this case, the source and the body, they are the same node, but I will just keep it for now. You don't have to draw the body. But let's keep it right now. And then you have the drains over here. Then basically you will have a current coming here. Let's call this one GM. VGS. Then you have another current over here, GMB VBS. Then you have another current over here, another resistor, let's call it. Well, some people call it RO, or some people call it GDS. So GDS is the inverse of the RO. And then you have the drain, you have the output, basically. So let's talk about what's the, actually let's forget about the output. Let's just focus on the small signal first. So what is the drain current exactly? The drain current is IDS. Remember that the current coming from the drain to the source is what we care about, all we care about. So the IDS is the current coming from this node to this node, which means there are 3 current actually flowing here. So what does this mean actually? This means this current GM-VGS is the current source, right? It means because of this voltage VGS, we have this current. And this GM, this current means, this is another color. And this current means because of the voltage VBS, we have this current. And this current means because of the voltage across D and S, we have this current. So there's something behind it. So in this case, we know there's a voltage across VGS. So this one will always be there. But VBS, they are actually the same node because the B is connected to ground. Source is also connected to ground. So we can ignore VBS because VBS equal to 0. So when VBS equal to 0, so this one will be gone. So we don't really need this term. But for some other term, when VBS is actually there, we need to consider about it also. So in this case, we don't care about it. Let's redraw this. Be ground because the B is over here. B and source are actually same node. And then we have only 2 terms left because there's voltage across VDS, of course. So the IDS will equals to GM VGS plus the voltage across the current coming here because of the, let me draw it better. Like, let's make the D over here. So the current IDS will be equal to the current coming here and the current coming here because of KCL. So IDS will equal to GM VGS plus, when the current across here will be the current is coming from VD flowing to VS. So it will be VD minus VS, which is just VDS, divided by RO. Another way to say that, because GDS is equal to 1 over RO, so we plus GDS over here, it will equal to VDS GDS. Let's make it GDS VDS. Some textbooks refer RO, some textbooks refer GDS, because I like to use GDS because we are considered transconduction over here, so we can just make it GDS. GDS and RO, they are the same thing, just a different way to represent this resistor. GDS means transconductance across drain source, DS drain source. So that's a small signal of this one.